us start. Today we have got a very interesting talk by Dr. C.C. Reddy. So Dr. C.C. Reddy does not require any introduction, right? But still, he is a very pioneer person working on, power. So he did his PhD from same place from where Dr. Manoranjan Mishra did, that is IISc Bangalore, and then he worked at J-Power System Corporation, Hitachi, Japan, and currently he's an associate professor at our institute, Indian Institute of Technology, and today he has got many honors, awards. And today he's going to talk about recent advances in reliability and life estimation of power equipment for an assessment of nanodielectrics. So let me tell you that Dr. Reddy is working with a team on power, and he has got a funding of 10 million Indian rupees, that is 1 crore. So this is a good opportunity to know about our faculty and build up collaborative projects, build up, do hand-holding with our faculty. So I welcome you, Dr. Reddy. Please start your presentation.
Thank you, sir. Thank you for this opportunity. I will share my screen first.
Yeah, good. You can see your presentation now.
Okay, sir. So good afternoon, everyone. So my today's topic of presentation is recent advances in reliability and life estimation, and that is for an assessment of nanodielectrics. So let us first remember our honorable former president, Shri APJ Abdul Kalam ji. So this lecture is dedicated to him. So let us also see what he said. Man needs difficulties in life because they are necessary to enjoy the success. So when anyone faces difficulties in life, they should not, get demotivated. That in future when successes come, definitely they will enjoy. So that is what his message to everyone. So with that, I also thank our director and our Dean Research for having such an excellent idea to start this APJ Abdul Kalam series of lectures, which are in fact an opportunity for everyone to know among ourselves what we are doing, and each other, we can know each other, and then this may lead to further collaborations and then further development of the institute. So with that, I will briefly tell about high voltage lab, and then after that I will go into research topics. So the high voltage lab is located at ground floor of JC Bose block, room number 101, and it is well equipped with experimental facilities. We have AC, DC, and impulse voltage generators, up to 400 kilovolts impulse, and we have best characterization facilities as far as solid insulating material is considered. As per the academic leadership, the lab was one of the pioneer. In fact, it produced first PhD student and then first MS and several gold medalists in our department. And as per the major events hosted or organized by the lab, we have organized the IEEE conference, international conference in Europa, right in 2017, and again another one in New Campus in 2018. So this was CATCON 2017. Actually, it was represented by several countries, and it was a successful conference in the old campus we have conducted. And again, one more in 2018 December, right after we entered into the new campus, this conference was conducted. And I wish to tell everyone that the 15th IEEE ICIAS 2020 is being conducted in November 2020. It is in virtual mode and call for papers was already issued. 26th to 28th November is the date of the conference. And the website is given here. And it is jointly organized by several colleagues across the departments. So this is about our lab. And then I would like to tell the research areas. And we are also open for collaborations across the departments and all. So on materials, we work on nanodielectrics, nano rubbers, nano esters, nanoplastics, and biodegradable dielectrics and composite dielectrics. So this is on material part. On systems, we work on power cables, electric vehicles, smart and micro gates, related topics related to high voltage and equipment related topics. And then on fundamentals, conduction, space charges, transmission transients, electric and thermal fields, breakdown, and life estimation. So among the latest topics, we are also contemplating on COVID-19 related projects with support from other colleagues across the departments. And the current topic is on life estimation, and it is related to nanodielectrics. So as per nanodielectrics, so in the context, a nanodielectric would consist of a multi-component dielectric possessing nanostructures, the presence of which results in the change of one or several of dielectric properties. So this was defined in way back in 2001 in one of the CIDP conferences. That was the first reference paper for us on nanodielectrics. So it actually consists of a base material shown in yellow color, and either nanofibers like this or nanoparticles like this are embedded into that. So the amount of nanofiller is normally very small. So as you can see on the right side of this slide, so the filler content on the x-axis that represents in PHR it is written here, parts per 100 parts of resin, 100 parts of base material. So just 0, 2, 4, 6, 8, 10, you can see this is just percentage, you can imagine. 2%, 4%, 6% of the base material. So when it is added to the dielectric material, the nanoparticles of this percentage are added to that one. A drastic reduction in conduction can be observed here. So this is actually original conductivity, and after that the conductivity with 1% it became like this, and after 2% a drastic reduction can be seen. So this is how the material properties, dielectric material properties get affected. This reduction in conductivity is important for dielectric engineers or high voltage engineers. For some it is the reverse actually. Increase in conductivity is important. So for us, we are interested in dielectric material, therefore reduction in conductivity is important. So in some cases, adding nanoparticles improved the conductivity where it was required actually. Here we use inorganic nanoparticles, basically MgO, SiO2, etc. So they possess this property that the conductivity decreases drastically with the addition of nanoparticles. You can see around 100 times reduction. The size of our nanoparticles, average size is 50 nanometers. So this was reported in one of the papers. So after that, we try to understand the conduction mechanism inside the dielectric materials, and this is the base material that was used for this nano composite was LDPE. We have used low density polyethylene. The low density polyethylene is base material for all cables, power cables that you find in transmission or distribution. So this is the base material, and in which these nanoparticles of MgO or SiO2 are mixed, and then nano composite is formed. So after that, we try to understand the conduction. So the conductivity experiments were conducted, and then this is electric field, and this is DC conductivity. With electric field, these the data points, squares and stars, are experimental data points. These are our experimental data points, and we try to match with several existing theories, popular theories. Schottky model, Poole-Frankel model, and thermally activated hopping mechanism and all. So we try to use those models, but none of them could fit to these conductivity which is experimentally measured. So after observing this, we have carefully gone through the problem, and then found out a solution. It is based on the structure of low density polyethylene. So this was proposed by Lewis. So we have extended the model by proposing that the interfaces between the spherulites need to be considered. So this is the LDPE material in which you can see the certain region in which this kind of structures will be there. Those are called spherulites. So inside the spherulites, so until now the amorphous region and crystalline region were considered. We have came up with interfacial region between these two, because it cannot be sudden divide. Actually, there will be sudden interface. So after carefully understanding the interface, and then its structural information we tried to obtain, and after that we came up with a conductivity model, and we have also observed the crystalline region very carefully, and among that these types of vibrations were observed, and you can see here. So among these, this type of vibrations, asymmetric stretching is observed to be dominant, and we have used all these dominant parameters to study to come up with a conductivity model, and then we obtained a best conductivity model which matches exactly with the experimental results. So this is about conduction. We have tried to track with the experimental results and with the theoretical thing. And after that, nanodielectrics, space charges were also investigated. Actually, space charge is the an unwanted charge accumulation inside the dielectric material. What it causes is if there is no charge inside the dielectric, if only polarization mechanism is there, dipoles are there, then the electric field inside the dielectric will be uniform, and there will be no enhancement in the field in any portion, at any portion of the dielectric material. But on the other hand, when the dielectric starts accumulating the charge, which is undesirable, so in that case, electric fields will become non-uniform. If it is non-uniform, for a given applied voltage, obviously somewhere it should be more and somewhere it should be less. So electric field gets enhanced in certain portions of the dielectric, so which will cause faster degradation and easier breakdown at lower value of overall the voltage. So that is what used to result in virgin materials. But when nanoparticles are added, you can see here three types of material. This is virgin material, the top one. This is a microcomposite, means the particles of micro-sized particles of same material were added. So in that case, the space charge behavior improved, but it is not improved as much as the nanocomposite you can see here. This is nanocomposite. Improved means, this is here, this is cathode portion, this is anode portion, and this is the, the portion in between is the, inside the dielectric material. You can see almost no charge accumulation inside the dielectric material. But in case of virgin material or base material, you can see lot of disturbance, lot of changes in the charge accumulation. Dynamic changes, in fact, were observed. So with this, electric field distorts like anything, and then breakdown will result. So microcomposites, of course, has some improvement. So with these three are reflected here. So you can in electric field. So here, this is the electric field of virgin material. You can see maximum electric field 190 kilovolt per mm. Whereas with 1% of nanoparticles, it got reduced to 150 kilovolt per mm. Around 40 kilovolt per mm is the reduction in electric field inside the dielectric material, is a significant change as far as its breakdown is concerned, as far as its life is concerned. So this is how nanoparticles also decreased the charge accumulation inside the dielectric material, which was reported in IEEE transactions. And after that, we also tried to understand, electric field and charge distribution inside the dielectric specimen, and came up with specific theory for that. And mathematical solutions were given for the electric field and then space charge by solving the differential equations, governing differential equations, which was reported in, again, IEEE transactions and dielectrics and electrical insulation. So as for the breakdown also, investigations were done. This was the MgO content, MgO filler content, which is 2%, 4%, 6%, 8%, 10%, you can see. So until certain percentage, until this time, this percentage, the breakdown strength increased, the DC breakdown strength increased. So several other properties like this we have observed, many other properties, for example, tree inception. So electrical treeing is known as, from sharp edges, the dielectric material used to break slowly, and the structures appear like a tree. For example, this is a sharp edge inside the dielectric material, and then from this edge, so the breakdown will start, and then it will propagate and reach the other electrode, and it will break. So this structure looks like a tree. So this is actually basic reason for breakdown of any dielectric material. So this tree inception voltage means at which this tree starts. So that voltage has drastically reduced in case of MgO, LDPE, nanocomposites. So this is, apart from this, impulse breakdown strength was also improved, and partial discharge inception voltage was also decreased drastically. Partial discharges means the discharges which are unwanted discharges that will be occurring inside the dielectric materials due to voids or contamination during the manufacturing process. So these discharges will ultimately degrade the dielectric material and cause the breakdown. So there is a particular level of voltage at which this inception of this partial discharge starts. So interestingly, the partial discharge inception voltage also drastically decreased in case of nanodielectrics. So as far as the properties of electrical dielectric performance are concerned. So several improvements were observed in pillars with nanofillers, but does it mean that nanodielectrics can replace the original materials or virgin materials, and then can we use them for power equipment or any other application? Of course, first nanocomposite cable has already been installed and it is working fine. But the question arises as to how to judge whether the nano dielectrics, we have seen a lot of improvements in the properties, are good for power equipment. So it is not necessary that once we observed initial improvement, which is tested in laboratory in 1 or 2 days, which cannot certify that the material can be used for long-term application where 30-40 years of usage is expected, life is expected. So this fundamental question actually need to be addressed. So there is a difference between initial and long-term performance. For example, so this is at t is equal to 0 at this corner, and this is vertical axis is voltage, and this is life. This kind of curves are volt time curves, or VT curves, or life curves. These are all called. Actually, on log scale, this is plotted. So you can see here there are two types of materials. This is virgin material or base material, you can say, pure LDPE without any nanoparticles, and there is a nanodielectric material. So at t is equal to 0 at this corner means initially after making the materials, if we test, the breakdown voltage of virgin material is low, but breakdown voltage of nanodielectrics is very high. So can we conclude based on this that nanodielectrics are better? But if we conduct long-term tests, and then if we see the VT characteristics, if after 30-40 years if we see, so if the slope of VT characteristic of nanodielectric is like this and virgin material is like this, you can see this is say operating voltage or design voltage. So at design voltage, the life of nanodielectric is 20 years, whereas the life of virgin material is 40 years. So what I mean to say is such a case may arise in case of nanoparticles, nanodielectrics. So a nanodielectric can have lesser lifetime than the base material. So traditionally, in high voltage or dielectric or insulation engineers, they see particles as a defect. But now we are saying that adding a particle, improving the properties. So we should not see it as a defect now. But what is the guarantee that it will not act like a defect over a period of time? So therefore, although better initial performance is reported, there is no guarantee for longer lifetime. So this essential, question need to be addressed before we go for actually using the nanodielectrics. So similar to VT curve, we have SN curve in other branches of engineering, where fatigue life NF versus stress level S is given by the SN curve, which is represented by NF into S to the power of M is equal to A, where A is called stress coefficient, M is called endurance, A is called strength coefficient, and M is called endurance coefficient, NF is fatigue life, S is the stress. Similarly, in electrical engineering, we have life L and voltage V. So L into V to the power of N equals to K, where K is again strength of the material. So this is how it looks like on this is voltage or stress, this is life or lifetime or life cycles. So on log scale, SN curve or VT curve is a straight line. So both represent straight line on a log scale. So the conventional, constant stress test, how to obtain such a curve in a laboratory or in experimental tests. So conventionally, constant stress tests were proposed and people have used them successfully, but the times involved will be in years actually to find out the characteristic of ST, SN or VT characteristics. The experiments will be very long-term experiments, which are called aging experiments, which will run typically for 1 or 2 years at least minimum. So after that, we have to say the nanocomposite is good or bad. So when we are actually doing some research for development or for improvement purposes, so waiting for so long will obviously delay the research, and then it will affect the research. So how these and one more problem with such kind of tests is, suppose at V1, if we are conducting a test, we don't expect a single point here. If there are 10 different samples, actually the 10 different samples will break at 10 different times. And then again, of course, there is a statistical or there is a probabilistic behavior that is observed, of course. But here, the longest sample sometimes can be in years. So the samples which are getting delayed sometimes or the experiment is stopped and then the data is processed, saying that it is censored data analysis. In that case, these samples which did not fail are not considered, and their probability is taken into account in the number of samples tested. They are also taken into account while deciding the probability of lower breakdown values. So this is how data analysis is done, but it is very complex and often suffers from inaccuracy. Not only that, it is longer time it takes, but also at the same time there are inaccuracies due to this kind of censorship. But can a material assessment wait for so long to decide? And can a manufacturing line wait for such an assessment so long? So this to avoid this, the accelerated aging tests were proposed in the literature. It reduces the time drastically actually. So time of estimation, not lifetime. Time of estimation, it is reduced. It reduces actually. So here, as you can see, this is time axis and this is the stress. The stress is increased in steps until the sample breaks. So this delta T is maybe fixed as short as few minutes to few hours, or maybe half a day, something like that, and stress level appropriately so that the breakdown can be obtained quickly. So, but the problem here is, the analysis is much involved as the aging depends on unknown coefficient n. So here L v to the power of n equals to k, or if it is in steps, this formula will apply. This is for continuous stress. This is for step stress. We have to apply sigma is equal to 1 to r. If r steps are there, delta Ti into Vi to the power of n equals to constant k, where n is unknown, k is also unknown. So this is a complex analysis, and then there were several reports which suggest usage of maximum likelihood method to obtain the solution of this equation. but the understanding was not adequate, and the results were not so popular. There were certain lacunas in the existing definitions and existing literature. So damage, the conventionally defined as N naught by NF, where N naught is the number of cycles elapsed, and this is NF is the number of cycles in life. This is lifetime. This is elapsed time. So this is how the damage is defined. So here, if step stresses are used with the different steps, this kind of definition, sigma I is equal to 1 to R steps actually, N naught I of each step divided by NFI, the life under that stress. So this kind of definition was used traditionally by, which is known as Minor's rule or Minor's law, or Palmgren-Minor's rule. So it precisely actually represents relative elapsed life, or per unit elapsed life. So with units as time, percentage of time, it is percentage of time that is elapsed. But there is no reference to stress here in this definition. So this is one of the lacuna. So after that, we carefully examined the damage, and it is redefined based on understanding of SN carbon. Then actually damage of any equipment or any material should not only depend on the time, but also this is time or elapsed time, but also the stress at which is stressed. So this s to the power of m we have arrived at using the by observing the SN relationship. So the damage is redefined like this. So in this A is actually strength constant, and here the damage actually represents elapsed strength rather than elapsed life. So this kind of definition we have used for the reason I will explain later. And alternately, since A is actually constant, is believed to be constant, alternately the damage can also be defined like this. So here it depends not only on the time, elapsed time, but also on the stress at which the time is elapsed. So at which the sample is tested. So the similar definition in electrical, this of course in fatigue stress, in electrical it turns out to be like this. So delta T and Vi to the power of N at which the stress is stressed, and I equals to 1 to R. So at the end of the life, obviously D equals to A. The damage equals to the strength of the material. So as the damage approaches the strength of the material, or entire strength of the material is elapsed, then the material would fail. So this is what is the revised definition, which takes care of stress also apart from the time of stress. So with this definition, we also observe one more thing here. See, the strength of the material, is it a constant? In the literature, A is reported to be constant. So if A is constant, then all materials should fail at a particular strength only. Or it means that all the materials or all samples that are made in a lot are having same strength, which is obviously not true, because same strength is not expected due to non-uniformities in the samples, maybe defect distribution or contamination or whatever it is. So there is a distribution of this strength. So that's what we have observed. So traditionally, either strength, S, or NF were proposed as random variables. But if you see carefully the equations here, which is the more correct random variable. NF into S to the power of M equals to A, and A was believed to be a constant, but NF was also a random variable and S also a random variable. So what we defined is considering A as constant is not correct, because all the experimental data whichever we have we have gone through until now, never this constant A is uniquely obtained for all the samples. It's not possible. There is a statistical distribution for A also. That is why we proposed the damage or strength constant. Damage equals to strength constant when it when the sample fails. Damage is proposed as the random variables. So random variable, and then the stochastic nature of the failure is attributed to the stochastic nature of the strength of the material. So means the failure times which are observed to be in practice to be distributed in a viable probability function as a viable probability function. So why these times are different for different samples? Because the strength is different for different samples. Maybe due to contamination or maybe due to non-uniformities, whatever it is. So we attribute all viable statistics to A instead of N and S. Because automatically N and S being functions of A, automatically such viable statistics will apply to N and S as well. So this is what is proposed. Of course, that we have worked in electrical quantities and reported in this paper, in one of our papers. One of my students has done this work. Of course, all papers are done by my students only. So after that, after proposing the damage as a random variable, so we have made the analysis of various aging tests that are being conducted. So there are different types of aging tests. So just now we have seen the step stress test and then constant stress test. So complete picture of all the tests are given here. So a withstand stress corresponds to simple vertical line, and then a step stress test corresponds to this this kind of behavior. This is actually log-log scale. In fact, the step size is uniform completely. So, but as since it is log-log scale, it will diminish as as you go up. So that step is not seen, but it is actually step stress test. So these three types of step stress tests with the different step sizes are given here. Similarly, this is a ramp test. Ramp test means simply the voltage is switched on and it increases in a ramp model until breakdown. So that is ramp test. So you can see two types of ramp tests we have plotted here. And then this is withstand stress test, and here life curves are given here. These are life curves. So we have not taken single life curve here because the SN characteristics or VT characteristics that assumes constant A or constant K. Instead of that, we are proposing a statistical spread of these life curves. So when we conduct an experiment, in fact, we will end up with data points. For example, we are conducting a step stress test like this. So we will end up with data points on this line at different positions, different points of time, different samples will fail. If we use same step test for different samples, so we will see a spread in the data like this. So this is what is proposed in our paper. So with this is actually this voltage and time characteristics. Similarly, we can see damage and time characteristics for the same types of tests. So here it is given in terms of damage. You can see all these are damage lines, parallel lines. So irrespective of time, this is time axis, damage will have certain spread, statistical spread of course, but irrespective of time, the samples will fail within the certain range of damages. After accumulating certain range of damages, that is statistically distributed. So that's what is proposed here. Now here this is step stress test 1, step stress test 2, 3, like this. If we conduct the experiments in a particular step stress test, we end up damages on this curve only. This is what is traditionally making the difficulty in obtaining the coefficient n using just single test. So we cannot in fact obtain the n, or n means coefficient, endurance coefficient n, by using a just single step stress test. We need to fit a damage line like this or damage curves like this for at least two different step stress tests or two different types of tests. For example, one step stress test like this, another step stress test like this, then we take, then you can have, you can observe the data, and then you can have parallel lines fitted for a particular value of n. So where the lines will become parallel, or where the 63% line or particular probability 50% line will become a parallel line. So that's what is proposed on the step test. So after this, we have compared the times also. Time of step test and time of constant stress is related like this. Time of step stress test is very small compared to constant stress test, which may end up in years, after years theoretically. So this will be typically very short time, maybe in 24 hours, something like that typically. So after showing the damage characteristics, how it changes in a particular with a particular step stress, we have proposed to use at least two types of tests that are needed to obtain the equalization of damage, because in these two types of stress we have to equalize the damage at a particular value of n. That n is the endurance coefficient of the material or equipment. So this equalization of course is very simple and effective once we conduct, for example, say this type of test and this type of test, which differ only by in a step time. For example, here 1 minute, 5 minutes, 15 minutes, 50 minutes tests are given. This is 1 minute, this is 5 minutes, this is 15 minutes, and this is 50 minutes test. So you can see there is a difference in the times of breakdown. So at least two of them are needed for obtaining the breakdown, and after obtaining the breakdown, we have to evaluate damage and with the variable n and equate the damages. Means at which value of n the damages are equal, that value corresponds to the endurance coefficient. So this has been proposed, and this is the flowchart of the procedure how to obtain to equate the damages, because this is the damage curves, these are the damage curves. So we have equated, say for example 63% of damage or 50% of damage. Traditionally viable 63.2% of breakdown strength we use in our high voltage testing, etc. So we did for 63.2% as well as 50%. 50% means it's a mean damage. So for these two, we have equated the damages for different step tests and ramp tests, and then proposed a procedure by which we can estimate the endurance coefficient L v to the power of n equals to constant, this n, the endurance coefficient, to estimate n very accurately. So we have, after finding this, actually the step tests are very fast. less than 24 hours, you can estimate endurance coefficient. So, but they have to be validated with long-term tests. We did do that. So the method actually successfully worked out for long-term tests on cable samples and then material samples as well. And it fitted well, very well. So after that, we have applied to our nano composites also, nanodielectrics also. So interesting results were found, which are actually under adjudication now. So I can only tell the sketchy results here. For example, we have two nanodielectrics, nanodielectric 1 and nanodielectric 2. So the difference here is only in the surface treatment, nothing else. Same nanoparticles, but with different surface treatment. So what is happening in one case? This is, at a time t is equal to 0. You can see both of them have almost same performance, but one is surface treated differently, the other one is treated differently. So in one case, in nanodielectric 1 case, the lifetime is lesser than the virgin material. This is virgin material or pure LDP material. But in the other case where in the nanodielectric 2, so the lifetime increased drastically. So it is even beyond 40 years. So the nanodielectric 2 with surface treatment appears to be a better material. So what it means actually is when we are mixing the nanoparticles with certain base material, obviously if there is no compatibility between these two materials, or there is no linking mechanism on the surface of the nanomaterial to the material matrix of the base material, then that material may be initially good. If we test the initial performance, initial breakdown strength, or initial conductivity, or initial tree inception voltage, all these things, maybe it behaves well, but in the long-term performance, it is not suitable because it fails. But this testing with the proposed method, damage equalization method, together with step stress tests, can be estimated. This behavior can be estimated typically in about 24 hours. We need not wait for 1 year or 2 years to assess the materials. So especially this is useful for when developing a new material, or this kind of test results are of utmost important for research labs, where we have to assess whether the material, of course, it performed well in the initial performance, but whether it will work for long term or not. So this method has been proposed and it worked well. So with this, I end my presentation. So yeah, thank you. So open for questions, please.